In our everyday life, we use a plethora of electronic devices and electronic interfaces, though a huge portion of it remains inaccessible to people with age-related or physical impairment. Remember how many times you heard from your dad or granddad that he is having trouble in using the new fancy smartphone? Or your elderly colleague is having trouble in using the new online rail booking system? You may also encounter similar issues when trying to use a touchscreen phone in a moving bus or watching a foreign language film without English subtitling. Inclusive user model is a representation of perceptual, cognitive, and motor abilities of user in a machine-readable form. The inclusive user model is implemented through a simulator and a set of user modeling web services. The simulator can help designers to understand, visualize, and measure effect of impairment on design. The web services can be used to adapt or personalize any electronic interface in runtime. The simulator has different modules to simulate visual impairment, hearing impairment, cognition, and motor impairment. Here is a sample output from the simulator, which can predict an approximate movement time, which is well validated through user trials involving people with different range of abilities. And it can also show the benefit of using different input adaptation algorithms. The simulator can help to visualize effect of multiple impairment on design. For example, the bottom picture is showing the effect of dry macular degeneration, color blindness, and Parkinson's disease on a single interface. The black spots are resulting from dry macular degeneration, while the overall color of the picture has been changed due to the effect of color blindness. The blue line is showing a probable cursor trace for a person having Parkinson's disease. As can be seen from the picture, the person is having trouble to stop pointer movement, which results in some random movement at the end of his pointer trajectory. The development of inclusive user model followed a user-centered design process, and at each phase of development, we involved a lot of end users as well as experts in the field of ophthalmology, occupational therapy, and psychology. The simulator has also been used to develop a set of user modeling web services, which are used to adapt interfaces in runtime. The user modeling web services work by creating a user profile. In this particular example, we are creating a user profile for a person having mild tremor in hand, as well as protanopia type of color blindness. We have used the Amsler grid to detect macular degeneration and plate 16 of Ishihara color blindness test to detect the type of color blindness. Once the user profile is created, it's stored in web, and it can be used to adapt interfaces across any device the user is using. The user profile is used to predict interface parameters. The user needs to log in with his username and password as usual. We also take the device type and screen resolution as input parameters to the model. These parameters are used to adjust font size and other parameters according to the device type. Here is a prediction for this particular user. In this example, we predicted the horizontal and vertical button spacing, which is the minimum separation between any two interface elements, the minimum font size requirement, the color contrast, and best input and output modality for this user. This page demonstrates the appropriate rendering for this user following the predicted interface parameters. The user modeling web services can render the same web page differently for different users based on their user profiles. Similarly, if the user is using a different device, say a smartphone, he can still get a personalized interface based on his user profile. Finally, this particular screen puts 3 different versions of adapted interfaces in a single screen with different button sizes, font sizes, and color contrast. Inclusive user model has been validated through a plethora of user studies involving users with a wide range of visual, cognitive, motor, and hearing impairment. We recorded eye gaze pattern, audiogram, and pointing movement trajectories of users and used those to validate different modules of the system. Research on inclusive user model has also contributed to develop new modalities of interaction, especially a gesture recognition system and an eye gaze tracking based system. The gesture interaction technique is developed by our colleagues at Fraunhofer IGT. We contributed in an input adaptation algorithm that attracts the pointer when it is near a target. This particular algorithm helps gesture interaction by people with slight spasm and tremor in hand, which is very common in elderly population. The eye tracking based system is developed at Cambridge University. Presently it's using Atobi X120 eye tracker, and the pointer moves in the screen according to the eye gaze of the user. We developed an algorithm to smooth the pointer movement, and we also integrated an scanning system which solves a few issues with traditional eye tracking based system. In this system, the user can seamlessly move between the eye tracking based system and scanning system whenever he wants, which reduces the eye strain but didn't slow down the speed of the overall system.